Now, I talked about this in the previous notes, but if you're looking at a solution to a system of equations, it's the point of intersection that I find if I were to graph the two lines. So really, in these, we're going to graph each of these lines carefully, and then we're going to go and look for the points of intersection. So, because this is in slope-intercept form, the constant is the y-intercept, which is where the line crosses the y-axis, so positive 4. The slope is negative 3, which I can turn into a fraction so I can see the rise over run by putting it over 1. I know a slope that's negative means the line falls as it goes from left to right. So if I go down 3, I need to go right 1. Now I'm going to carry that pattern across my graph because we need to be pretty precise with these graphs to make sure we find the right point of intersection. So I'm going to make sure I put arrows at the ends of both lines, and I'm going to draw my line through those points. Again, easier to do. We should be using a straight edge. Easier to do on the paper than it is on here. And then my second line crosses the y-axis at negative 5. A positive slope means this rises from left to right. So the slope is 6, which I can turn into a fraction by putting it over 1. So I'm going to rise 6, run 1. If you do this correctly, we are not going to give you any wacky, weird graphs where the answer is a fraction. So look for, if you draw these correctly, a nice integer solution. And then you need to actually write the answer. The answer is the ordered pair 1, 1, because this is where x is 1 and y is 1. Again, this one is in slope-intercept form. It crosses the y-axis at negative 4. The slope is positive 1, which I can turn into a fraction by putting that over 1. So positive rises from left to right, up 1 over 1, which is like up 2 over 2, and so I'm going to kind of make this a little bit faster. And then draw my line through those points. Second line is in standard form. Well, if we substitute 0 for x, 3 times 0 is 0, and we get the equation 3y equals 6, divide both sides by 3, so y equals 2. So the point 0, 2 is on this line. If instead we substitute 0 for y, this part becomes 0, and I get the equation 3 times x equals 6, divide both sides by 3, and x equals 2. So the point 2, 0 is also on this line. So if I look at what's happening with this slope, and I keep going down 2, over 2, up 2, over 2, I get a nice set of points to be able to draw my line through. And what I find is that I get this gorgeous point of intersection again. And that is the point where x is 3 and y is negative 1. So be careful with your graphs, and then also be careful when you're finding that point of intersection. This one crosses the y-axis at negative 2. It has a slope of positive 3, which is like up 3 and over 1, because it should rise as it goes to the right, or down 3 over 1 to the left. I'm going to draw my line through those points, and then graph the second one. This one crosses the y-axis at positive 1, also has a slope of 3, which means it's never getting any closer to that other line. Look at it. The x distance here is always 1, 1, 1, 1 from each of those points. These lines are never going to intersect, which means they're parallel. If they're parallel, think about it. The solution is the ordered pair for the points of intersection. There's never going to be a point of intersection, so this one is no solution. And the reason it's no solution is because there are parallel lines, which means they never intersect. So if you see parallel lines, that says no solution. This one crosses the y-axis at positive 4, has a slope of negative 2, so again it falls from left to right, so down 2 to the right 1, down 2 over 1, carry that across my graph to get a nice line going, nice setup for my line, I should say, going. And then when I go back and graph the other one, it's in standard form. So if I substitute 0 for x, I get the equation positive 2y equals 8. And when I divide both sides by 2y equals 4. So the point 0, 4 is on my line. Now I'm going to go back and I'm going to substitute 0 for y instead. So this part becomes 0, and I get the equation 4 times x equals 8. Then when I divide both sides by 4, x equals 2. Wow, you know what? In this case, when I graph that line, it turns out it's directly on top of the first line I graphed. So they're really the same line. If a solution is a point of intersection, every point on one line is shared with the other line. And there's an infinite number of points on a line, so this is infinitely, which is infinitely, many solutions. And the reason that it works out that way is because it turns out it's the same line. So infinitely many solutions. Go ahead and pause this for just a minute. See if you can do this one on your own, and then come back and check your answer. So the first one crosses the y-axis at -4. A positive slope is going to rise from left to right, so a rise of 1 and a run of 4, and I'm going to draw my line. And hang on, I got to fix this a little bit. Then this one crosses the y-axis at -1. A negative slope falls from left to right, so down 1 over 2, down 1 over 2, and I'm realizing that I probably need to fix this. Oh, I see what I'm doing. I'm going down 2 and over 1. See? It's important to be careful. Down 1 and over 2, down 1 and over 2. And remember, I said I'm going to give you ones with gorgeous points of intersection. So if you find that your line's doing what mine was doing, there's something wrong, because it should be a nice integer point. So in this case, x is 4 and y is -3. Make sure that you write your solution as an ordered pair. Thanks, guys.